Welcome to this application presentation of DIC, or digital image correlation, being used for axial and biaxial tensile testing. Here is an overview of the applications that will be presented in the axial and biaxial tensile testing presentation. Applications include that of a steel bar tensile test using the multi-camera DIC system, also of a cutout steel bar as well with the flex DIC system, the measurement of a biaxial cruciform aluminum alloy using the flex DIC system, measurement of a 3D printed structure, of a composite laminate, of shape memory alloy, a plastic polymer in conjunction also with an infrared camera, and also a PVC coupon, and also a cylindrical specimen as well. Application 1 was a steel bar tension test measured using the multicam DIC system. The test object was a steel bar of a rectangular cross-section. The width was 10 mm with a thickness of 5.5 mm. The measurement objective was to measure the thickness of the steel bar via a double-sided or biplanar setup. The second measurement objective was to determine and measure the Young's modulus and compare the Young's modulus with the input Young's modulus. Measurement objective 3 was to compare the UTS between the engineering and true stress assumptions. Objective 4 was to measure the plastic strain ratio, or the R value. To the right, we see the individual fields of view for cameras 1 and 2 from the front side and cameras 3 and 4 from the rear side. Presented in each of the fields of view is the ISTA40 2D overlay visualization of the Lagrangian principal strain 1, or major strain in millistrain. The advantage of biplanar or double-sided DIC measurements is that they can provide detailed information on specimen bending and misalignment during a test, which would otherwise not be accessible using a planar or single-sided setup. The different strain distributions on either surface indicates bending or misalignment of the steel bar in the materials testing machine with respect to the loading axis. It can be seen in the video the increasing Lagrangian principal strain concentrates at the center of the specimen right up into fracture. In video 1 shown to the right, we see the ISTA40 3D visualization model of the Lagrangian principal strain 1 in millistrain with one biplanar virtual point gauge. The temporal plot below shows the thickness difference between the two biplanar points in millimeters with respect to acquisition step. During the end of the tensile test, the coupon specimen undergoes necking, which can be observed as a drop in specimen thickness. The double-sided measurement allows the true stress to be determined through actual measurement of the specimen thickness, rather than using the engineering stress on the basis of the constant volume approximation of the Poisson ratio. In the QR code linked on the bottom left, users can scan and download the double-sided testing application note. In figure 1 to the top, we see the ISTA40 3D visualization model of the displacement with reference step shown in green and the failure step shown at maximum load in red. In video 1 to the right, we see an ISTA40 3D visualization model of the displacement with rigid body motion removed, with the reference step shown in green and the acquisition step shown in red. The temporal plot below shows the load in kilonewton recorded as an analog input with respect to the acquisition step. it is clear that during the measurement the sample is misaligned in the materials testing machine with respect to the loading axis and as such bends. In Figure 1 to the right, we see the materials testing package with the advanced graphical user interface that allows users to plot a diagram of stress versus strain, also the Young's modulus, and saves the data series using one line gauge. The graphical user interface calculates the Young's modulus and finds the yield stress and strain, the 0.2% offset yield stress and strain, the ultimate tensile stress, and also the uniform proportional elongation. Users have the option of defining the cross-section geometries, being a circular or rectangular geometry, and the input dimensions, as well as selecting the stress calculation method based on either the engineering stress or true stress. The measured Young's modulus is 180.57 gigapascals, and the reference Young's modulus for steel is 180 gigapascals. The engineering stress was 595 megapascals, but the true stress was 680 megapascals. In the graphical user interface, users can define the dimensions of the cross-section, the stress calculation method, the strain range to be plotted, the determination of the yielding points, and also the range for the determination of the E-modules. In Figure 1, we can see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1 with one virtual line gauge called line 1. The gauge element is used to calculate the plastic strain ratio, using the ratio of true strain in the width to the true strain in thickness when a specimen is pulled in uniaxial tension beyond its elastic limit. This approach assumes the volume is constant during the tests and uses the true principal strains for calculation. In graph 1 to the top, we can see the 2D plot of 248 R-value data points with respect to the true principal strain 1. The average R-value is approximately 0.8. Application 2 was a tension test performed of a steel bar with a circular cutout measured using the Flex DIC system. The flat bar specimen had a width of approximately 60 mm and thickness of 6 mm. The material was steel 18 G2A2. The measurement objective was to compare the measured strain from the strain gauge above the circular cutout with respect to the DIC measurement. In Figure 1 to the right, we see the marked location of the strain gauge on the rear side, identified by the pink arrow. In Figure 2 to the left, we see the test set up with flat bar sample of the front side mounted between the two hydraulic grips. In Figure 3 to the top, we see the ISTRA 4D 2D overlay visualization of the engineering tangential strain Y in percent with two virtual line gauges and one polygon gauge. In Table 1 below, we can compare the measured strain of the strain gauge and the maximum tangential strain in Y on the polygon gauge, which is adjacent to the strain gauge on the other side. Results clearly show that the measurement results attained using either technique deliver a low measurement uncertainty of less than 0.00055%. This application is a biaxial test performed of a cruciform, which is a fillet radii aluminium alloy sample. The biaxial test measurement objective is to measure and compare the principal strain 1, or the major strain, within the four identified areas A, 1, 2, 3, and 4. The second objective is to measure and compare the Z displacement along the two lines L1 and L2. In Figure 1 to the top, we can see the camera field of view of the cruciform fillet radiate aluminium alloy sample with the marked areas A1 to A4 and lines L1 to L2. In Figure 2 below, we see the ISTRA 40 2D overlay visualization of the Lagrangian principal strain 1 in percentage. The principal strain reaches a maximum of 37 to 38% in regions A1 to A4. As expected, the principal strain is near 0% at the center of the specimen. In graph 1 to the left, we see the principal strain in percent of each areas 1 to 4 marked. Each polygon gauge measurement strain as a mean value across the surface. The max strain A4 is 37% and the minimum strain A2 is 33%. In video 1 to the left, we see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1 in percentage. We can see the strain is concentrating inside the indicated areas A1 to A4. In Figure 1 to the top, we see the ISTRA 4D 2D overlay visualization of the contour best plane fit deviation, or the BFP, in millimeters with the marked lines L1 to L2 as virtual line gauges. The distribution of contour deviation is maximum plus 0.44 millimeters to a minimum of minus 0.32 millimeters. In graphs 1 and 2 to the right, we see the spatial graph of the Z coordinate of the respective lines at various acquisition steps. It can be seen throughout the test that the Z deviation develops in the form of a wave. In video 1, we see the tensile test application of a complex 3D printed structure using the FlexDIC system. In this example, the strain can be resolved down to 2 millimeters, whereby the maximum principal strain 1 or major strain is 50%. The iterative algorithm of the ISTRA 4D DIC software provides an unsurpassed high spatial resolution. This helps to resolve local strain gradients in static or dynamic deformation and strain measurements. This video is courtesy of Limas Messtechnik and Software GmbH. Application 5 is a composite laminate tensile test performed measuring using the FlexDIC system. The component is a composite fiberglass laminate specimen. The measurement objective is to evaluate the stress concentration direction during the tensile test. In Figure 1 to the top, we see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1 in percentage. The direction of strain concentration from the tensile test indicates the stiffness variation, or the anisotropy, within the specimen. It appears that the specimen was manufactured with a plus-minus 45 ply layup. In Figure 1, we see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain in the x direction. The direction of tangential strain was defined along the loading axis. DIC can provide detailed full field strain resolution, spatially resolved, about the progression and mechanics of crack propagation. Application 6 is a shape memory alloy tensile test performed under cyclic loading from 0% unloaded to 7% loaded strain using the FlexDIC system. The test object size was 33 mm in length and 3 mm in width. The measurement objective was to evaluate the Luda bands, or the slip bands, of the shape memory alloy through observation of local changes of strain under one loading cycle. In video 1 to the right, we see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1 or major strain in percent. In this video, it is clearly visible to see Luda bands or slip bands of localized plastic deformation on the specimen surface, which is common in shape memory alloys. The bands start at clamping and move towards the center of the specimen at an angle of 45 degrees. In graph 1 to the left, we see a temporal plot of the tangential strain x in millimeters versus the acquisition step time in seconds. The positive direction is defined in the direction of loading. Multiple virtual gauge points were used along the specimen to analyze the strain. It is clear that the strain moves in phases at different acquisition steps throughout the test. It can also be seen that the strain completely recovers after unloading. Application 7 is a tensile test of a plastic polymer coupon specimen. This test was measured using the FlexDIC system in conjunction with an infrared camera. The measurement objective was to evaluate the strain and temperature of common points on the specimen during the tensile test. As can be seen in Figure 1, a schematic diagram shows the test setup with the FlexDIC system and infrared camera. Users can also scan the QR code to get an application video of the infrared camera conjunction working with the DIC system. Video 1 shows the infrared camera analysis applications package graphical user interface with the full field 2D overlay visualization of the principal strain 1 in millistrain and the visualization of the temperature in degrees Celsius. The coordinate systems from DIC and infrared cameras can be unified and common virtual gauge point elements on the test measurement surface can be identified. 3 point gauge elements were created, and the major strain being the blue line and in temperature the red line values are plotted in the temporal plot below. Application 8 is a tensile test of a 3-camera FlexDIC system of an aluminium coupon specimen with a length of approximately 55 millimeters. The measurement objective was to investigate the approximated error radius, attributing to the measurement uncertainty of the contour between using a 2-camera and 3-camera setup. In Figure 1 to the top, we see a schematic diagram of the test setup with 3 cameras. In video 1 to the right, we see the EduDIC 2D overlay visualization of the Lagrangian principal strain 1 in millistrain with 1 polygon gauge element. The max strain of the sample during the tensile test is 2600 millistrain. In Table 1 to the top, we see the EduDIC 2D overlay visualization of the same test measurement step using identical evaluation parameters of the approximated error radius of the contour in micrometers. The maximum visualized result is shaded red. The minimum result is shaded blue. A facet size of 17 pixel and a step size of 8 pixel is used for the evaluation criteria of the unloaded step within the elastic tensile testing range. The contour error shows the full field accuracy specimen error of the contour, which is the lowest using the 3-camera setup, as can be seen in the top row. Based on the 3-camera digital image correlation system, we will obtain increased measurement accuracy and reduced noise due to the reduced influence of inhomogeneous illumination or reflection of light on the specimen surface, better 3D correlation calculation, specifically yielding a smaller 3D residuum due to an additional camera viewing the specimen from a different angle, and better tolerance against unexpected specimen shaking or image blur due to increased camera numbers. Application 9 is a tensile test of the PVC coupon specimen with the Poisson reference ratio of 0.39. The measurement system used for this application was an EduDIC system. The measurement objective was to measure and compare the Poisson ratio of the PVC sample using the materials testing application package, which is available for download via the e-learning platform. In Figure 1 to the top, we see the ISTA4D 2D overlay visualization of the Lagrangian tangential strain in the x direction in millistrain, with one polygon gauge element. The x direction was defined in the axis of loading. The polygon gauge element is used to calculate the Poisson ratio. In graph 1 to the top, we see the blue longitudinal EXX and green transversal EYY strain in millistrain versus time. In graph 2, we see the Poisson ratio versus the longitudinal EXX strain in millistrain. The measured Poisson ratio is between 0.38 to 0.42. As such, this compares well with respect to the reference ratio of 0.39. Application 10 is a tensile test performed of a cylindrical metallic coupon specimen with a length of approximately 45 mm. This measurement was performed using the FlexDIC system, and the measurement objective was to compare the measured strain from a clip-on axial 25 mm gauge length x in centimeter with respect to a virtual DIC line gauge. The second measurement objective was to investigate the specimen misalignment. In video 1 to the right, we see the ISTA4D 2D overlay visualization of the engineering principle strain 1 in millistrain with one line gauge element, line 1. An advantage of digital image correlation, or DIC, is that full field results and virtual gauge x in centimeters can be measured and results easily visualized. Shown in the pink arrows is the clip-on x in centimeter connection grips. In graph 1 shown to the top shows a temporal plot of the line strain in the millistrain of the line gauge element line 1 with respect to the test step acquisition. The black line is a measured x in centimeter feedback from the clip-on gauge as read in from the analog input into the DIC digital image acquisition controller. The difference between the measured result from the digital image correlation measurement and the clip-on x in centimeter is negligible. The test result indicates that the comparable measurement uncertainty is low between the tactile and optical DIC measurement system. Figures 1, 2 and 3 on the top from left to right show the ISTA4D 2D overlay visualization of the displacement in x, y and z in microns at maximum load. The x-axis coordinate system is placed on the axis of load application in the direction of elongation. The asymmetry of the y and z displacement indicates misalignment with respect to the axis of load application, and the gripping of the specimen by the x in centimeter, and/or within the testing machine grips. In the case of the y displacement, it is clear that the sample has undergone torsion. In video 1, shown to the top, we see the ISTA4D 3D visualization model of the displacement with widget body motion removed, with the reference step shown in green and the acquisition step shown in red. From this video, it is clear that the gripping influence of the mechanical x in centimeter causes outer plane deformation and bending to occur. Here is an overview of the following applications that will be presented: of a microspecimen measured using the FlexDIC, of an aluminium coupon measured using the FlexDIC, of bonded plastic foil, and finally of a shaped memory alloy performed with a FlexDIC and stereoscopic microscope. Application 11 is a microspecimen measurement performed using the FlexDIC system. In video 1 to the top, we see the 2D overlay visualization of the engineering principle strain 1 in millistrain with one line gauge element, line 1. The virtual line gauge element was used for the strain plot, shown on the blue line, and the corresponding load signal, shown on the green line, as a read-in from the analog input into the DIC data acquisition controller. In figure 1 to the top, we can see the stress in millipascals versus strain in millistrain from the measurement, which is included in the materials testing application package. Extracts of the ISTA40 2D overlay visualization of the engineering principle strain 1 in millistrain can be seen showing the strain development. Application 12 is an aluminum coupon tensile specimen measured using the FlexDIC system. The test object size was 200 millimeters. The measurement objective was to measure the principal strain of the specimen at point of fracture. In video 1, we see the ISTA40 2D overlay visualization of the Lagrangian principal strain 1 in millistrain with one line gauge element, line 1, in the left and right camera. A temporal plot of the Lagrangian line strain in millistrain was made with respect to the acquisition step, indicating a linear application of force until a peak is reached at 370 millistrain. A spatial plot of line 1 was also made of the developing concentration of strain localization, indicating the necking that occurred during the tensile test. Application 13 is a bonded plastic foil tension test measured using the FlexDIC system. A tensile test was completed using a test speed of 80 mm per minute. A trigger signal initiates the test when a preload of 10 newtons is reached. A ring buffer recording is then performed at 1 Hz. Two-section bonded plastic foil specimen was used for the measurement. In figure 1 to the right, we see the picture of the two-section bonded foil specimen with the load indication F. In figure 2, we see the picture of the test setup with the FlexDIC system. As can be seen, the specimen is mounted in T-mechanical grips. The measurement objective was to measure the strain concentration and elongation in percent around the bond interface between the two sections at failure. Graph 1 to the left shows a graph of the strain versus force in newtons, indicating that the bonded plastic foil elongated up to 200% before failure. The start length of the sample was 100 millimeters, and the final length was 300 millimeters, indicating 200% strain. Figures 3, 4, 5 and 6 show the ISTA40 2D overlay visualization of the Lagrangian tangential strain in Y in millimeters per meter. The Y direction is defined along the axis of loading. In figures 3 to 6, indicated in order according to the pink arrows shown, users can see the development of the strain concentration around the bond line. The peak strain was approximately 1,200 millimeters per meter, or 120%. Application 14 is a measurement of a shape memory alloy performed using a FlexDIC and microscope. This application is actually of a 2D DIC measurement. As such, only one camera was used. The test objective was to determine the X displacement and EXX strain under lateral loading. In this test, the in-plane lateral microtension loading stage was applied with an observation field of view of approximately 0.7 mm by 0.5 mm under the microscope. In figure 1 to the top, we see the camera field of view of 0.7 mm by 0.5 mm. In figure 2 to the left, we see the test setup depicting the single camera and microscope. In figure 3 to the right, we see the ISTA40 2D overlay visualization of the X displacement with rigid body motion removed in micrometers. The maximum X displacement measured is 11 micrometers. In figure 4 to the right, we see the ISTA40 2D overlay visualization of the Lagrangian tangential strain in the X direction in percent with rigid body motion removed. The maximum X tangential strain is measured to be 4.5%. This concludes the materials testing axial and biaxial tensile testing application presentation. If you have any questions or comments, please contact your local Dantec Dynamics sales representative or email product@support@dentechdynamics.com.